Hey, Brian Duggan here, aka Scooter 500, and this is a video demonstration of a project I've been working on called Miniature Rotary Phone. So this is the Godot port of the steering behaviors code I've developed for my game engines course from Unity to Godot. So it's a Godot version of things like seek, arrive, flocking, and path following, and things like that. So here we go. It's running in Godot 4.3 beta right now. I'm going to hit the run button here and give you a demo of the project. So I'm going to press F to make this go full screen firstly. So this is the first example scene in the project. This is demonstrating the seek steering behavior. And the seek steering behavior basically, some prerequisites, I guess. First of all, this behavior code was developed originally by Craig Reynolds, and he published papers in the 80s and also did a keynote presentation at GDC in 1999 and documented all of these behaviors for autonomous characters in video games, movies, and simulations. And his work has been really influential. It's been used in many commercial games and many movies as well. So it's based around the idea of an autonomous agent, which is called a void. And the autonomous agent keeps track of things like its position, velocity, acceleration, and then the void has a list of behaviors that are active. And those behaviors then are weighted and prioritized. And so you can get all kinds of cool emergent things that look like they are alive and unpredictable kind of behaviors. And also quite lifelike movements, which can be used to simulate things in nature, like birds and fish and so on, but also to simulate things like spaceships flying around. And so all the demonstrations in this project have a procedural creature, which you can see the camera is focused on right now. And also there is a spaceship in the scene as well, which I will show as well. So what is happening here? This is a void with one behavior active, and this behavior is called seek. And what's happening here is on a timer, a new seek target is being generated, and the void you can see there is seeking the target. What you can also see is that its movement is pretty natural. So each of the body segments, it's using a sort of like a procedural spine animation system. So they will kind of lerp and slurp their positions and angles so that they all try to line up behind each other. But it happens nice and slowly, so it looks like a spine. And what else can I say here? Also, you'll notice as the void is moving through the scene that it's turning very naturally. And well, let's see, what else could we say here? Also, it's banking to the left and to the right. So this could be used for spaceships or also things like birds and fish and so on. So you want to like have the idea that there's gravity, that there's a centripetal force, and a centrifugal force, I think. But basically, the void is moving through the environment. And if it's got a target over here, then it will bank over this way and then level out like this. So you can see that in the video there. All right, so a few other cool things I can do here. And this works for all of the demos. I can press C, which switches to a different camera mode. And in this camera mode, basically the camera becomes the void. So you can see what it's like to be a void. Pressing C again will release, and now I'm in first person camera mode, and then I can actually explore the scene. So what I wanted to show you here is the fact that there is actually 3 voids in the scene. This is the spaceship one to show you that these behaviors work really well for creating things like space games or things where you want to have spaceships flying around. Space battles is what my students would have used to simulate in the past. So you can see there's a little spaceship doing the seek steering behavior. And there's a third void in the scene you can see here, which actually doesn't have a mesh. And the third void is actually used to generate the camera, or basically to attach the camera to. So you can actually use these as well for really cool procedural cameras as well. So I'm going to press C, and now the camera becomes a void, implementing a behavior called offset pursuit. So we'll always try and maintain the same relative distance to the target, and we'll also avoid obstacles as well. So you've basically got a really good third person camera there as well. So that's seek steering behavior. All right, what else can we do here? I'm going to go on and show you the next behavior. Next one is called arrive. So with this behavior, the voids will have a slowing circle. And instead of like always trying to reach the destination at maximum speed, when they're inside the slowing circle, voids will gradually decrease their velocity, or try to decrease the velocity, just like something would do in the real world. It will generate a deceleration force when it's inside the slowing circle. So outside the slowing circle, it's going to try and reach maximum velocity. Inside the slowing circle, it's going to basically ramp down the velocity from max to the zero velocity when it reaches the destination. And you can see that also in the video as well, because what you can see in the video is that yellow line, which is sticking out the front of each of the voids, and the yellow line is an indication of the force. So you can see that it's going towards the target, and now you can see when you're inside the slowing circle, it is going to go in the opposite direction. So it's going to generate a deceleration force, or a force in the opposite direction to the direction that the void is traveling, and that will cause its velocity to decrease then over a number of frames, and gradually it will come to a stop as it reaches the destination. So that's arrive steering behavior. Let's take a look at the next example. The next example is a path following behavior. So with this scene, both of the voids are following a path, and the path is set up in the scene. In fact, I think I can show you this if I go Control. Is it Alt and 2 here? Let's see, did that work? I'm going to press Escape, come over here, just to show you how this is set up. If I go Alt and 2 here, Control and 2. Great, this is what I want. It's Control and 2. So I'll show you in Godot what that looks like. That scene is called Follow Path. So let's go to Follow Path. And you can see that the path here is, let's see, where's the path? It's a path 3D. So it's a path 3D. Yeah, and that's the path that's being followed. And now the path 3D, oh yeah, you add the waypoints to the path 3D node, and then yeah, the path is drawn there. I think there's a path drawer node that is drawing the path. Excellent. And yeah, there's the path. The paths in this example can be, if I go, it's Control and 1 again, hopefully. We're going to get back to the original. Let's double check OBS is working correctly. Yeah, we're back. Excellent. Back over here, follow path here. Okay, so the path can be looped or not looped. So you can reach the final destination node and come to a stop, or the void can, or it can loop back, and the path then goes back to the start again. All right, so this is follow path. Next behaviors I have here, bring my mouse over here again, pressing escape here, left arrow, and now I have two wandering behaviors. So these wandering behaviors are based on the original wandering behavior, I guess, from Craig Reynolds, and then I learned it from Matt Buckland's Programming Game AI by example. But the idea is that you sort of project an imaginary sphere in front of the void, and then you have some point on that imaginary sphere that the void is seeking, and then you have some algorithm then for moving the point around the outside of the sphere. So with this example that you can see in the video, the void is implementing, it's using kernel noise to create an angle. So the kernel noise is mapped onto an angle, and the angle then is letting a point, oscillate around the I suppose the forward vector of the void. It's oscillating around that to the left and to the right on that sphere. And what else can I say here as well? Yeah, it's also parameterized by the size of the angle. So you can have a small little one like this, where you can say have a big angle, and then allow the point to kind of like oscillate in a much bigger arc around the sphere. So this can be used to simulate all kinds of underwater life forms like dolphins, whales, anything that swims like this, left to right. Or also, I'll show you later, you can actually parameterize this as well, so generate the up and down. But this is kind of really good for, I use this for simulating a whale in a project, and it works really, really well. So, but you can combine it as well with other behaviors, right? So let me press C, press C again. I'll show you the other wander behavior. And this is the other wander behavior, which is the original one. This uses a concept called jitter. So basically there's a point projected onto the sphere, and there's a distance parameter as well. And that point then is allowed to move around. So it sort of has a jitter every frame, so it moves up and down, so on. And the behavior can be parameterized by the distance and the radius. So you can create all kinds of cool different sort of wandering effects. I think I have some more examples of wandering later. All right, next example. This is really interesting here because this scene, the void has 3 behaviors active. By the way, you can see the active behaviors printed in the top left of the screen there. So this has avoidance, constraint, and player steering. So avoidance means avoid obstacles. And you can see that there are 5 raycasts illustrated in the scene here. And these 5 raycasts are projected forward from the void. They're on a timer as well, so they don't happen every frame, and that's why you can see that they don't get updated every frame. But you can move the void around. The 3 behaviors to constrain is this. It basically keeps the void inside that white sphere that you see. And the 3rd behavior is called player steering. So player steering means take input from a game controller and generate steering forces from it. Now I think this is it. So if I pull these 2 triggers, I'm generating a velocity. Let's see, player steering. No, maybe it's not that. Maybe it's this one, this one, this one. Forward, that's what it is. Okay, cool. So forward on my game controller generates a forward force. Left stick then generates left force and right force. So I have control now, and I think I can also generate upward force. Yeah, using right stick I can generate upward force. So what's interesting to observe in this example also is that the behaviors are weighted and prioritized. So if I try to do something like drive this creature into one of the obstacles, the obstacle avoidance will take a higher priority. Now I'm going to try and do that, and then I will pause it to show you how that works. So hopefully I want to try and hit an obstacle here. I want to see this void hitting an obstacle. So to go forward, I need to do some generating force, and then once I hit something, I'm going to press P. So I can press P, press C, and C in the example. I'm back into first person mode here. Okay, maybe I'll try keyboard and mouse. We unpause void, let it go forward. I can see it colliding there. Yeah, there we go. Alright, so it's collided now with an obstacle. One of the, these are referred to in Matt Buckland's book as feelers. I think that word probably comes from Craig Reynolds' original paper as well. But these feelers are projected forward from the void's position every frame. Sorry, not every frame, on a timer. You can see it here. What's interesting to observe is you can get right in close here to see exactly how this behavior is working. And the little blue arrow is showing the normal of the colliding, what is it, the colliding triangle. So there's a colliding, the ray basically collides with one of the triangles. You get the normal of the triangle, which is basically a unit vector that will tell you what direction the triangle is. It's perpendicular to the surface of the triangle, like that. So you get the normal, it's the blue line there, and then also the red line is the force that's generated. And this scene, I think, is called, there's written on the thing, it's hybrid, no, player steering. What I want to show you is this. Let me go to open scene, player steering, LMNO, player steering, here we go, awesome. You can actually change the direction of the generated force. So I'm in Godot here. Control 2, I think I can show you Godot. Let me see, did that work? Oh man, I think it did work. Okay, cool. So I'm in Godot, and I can go to the avoidance behavior and say, instead of generating the feeler directions from the normal, I can use the incident, which is the angle of the incident. In other words, the reflected angle in the normal. You can do that one. I think I should be able to change it here. Yeah, there we go. So now I got incident, and the game is updated 5. with the new value there, and now I'm getting angle of incident force getting generated, and you can see it from the if I come over to the game again, press escape, you can see it from the gizmo that gets dropped. That's the angle of incident. Come back over here to avoidance. This can also change to, for example, the up vector, in which case you're always going to try and steer upwards around obstacles, but one that works really well for me is normal. So let me just resume playing that one. Pause running project, so I want to unpause. Oh yeah, it's unpaused. It is unpaused. It's actually the project is unpaused with the P button. All right, so that's called player steering, and that's an example of how you can combine steering behaviors together. Great. Next example. Again, Godot's so cool. I can actually save the file here as my game is running, and the game updates live with new code or whatever changes I've made. Let's see if I'm switching back over to controller 1. I think I should be switching back over to Godot now. Great, excellent. So, next example. Ooh, my game, I should say. Okay, click the button over here, press escape. Next example. Okay, this is just an example of showing how you can take one of these autonomous characters, autonomous agents, voids, and modify its values, modify the parameters on the algorithm as the void is actually doing its behavior, and you can observe it in its environment and then change it. So it's kind of a way of creating, designing and like crafting one of these creatures. You can add the behaviors dynamically at runtime, remove them, but also you can change the parameters. So what I'm going to do here is press escape over here, and just created a simple little user interface here where you can see, for example, I can increase the distance, and this basically increases the distance that the void projects forward the center point of the kind of like sphere for this behavior, which is called harmonic. So this is a very interesting behavior as well, because this uses the same principle as the wandering behaviors, but it uses a sine wave. So we'll just generate up and down motion or left and down motion for anything you want to create, a creature or whatever. So let me show you vertical, because vertical looks really good. What happens with vertical is you can see that the point is projected upwards and downwards. You get a different character of, if you like, emergent creature. So now this is a thing that swims up and down. You wanted to create a fish, for example, as opposed to something that goes with a left and right motion. And some creatures go left and right, some creatures go up and down. Let's press escape here. I'll also show you that you can change the radius here as well. So that increases the size of the radius by changing these parameters, dynamically changing the way the sort of like this is all procedural animation. It dynamically changes, if you like, the procedural animation to give a different sort of feeling of it being a different kind of creature. All right, what have we got next? All right, this example is a behavior called offset pursue. And with offset pursue, one of the voids, you can see the one at the front there is designated as the leader, and the other voids are designated as followers. The followers will try and remain in formation or with the same relative offset to the leader. But this behavior is kind of cool because it doesn't just calculate the offsets at the beginning and then try to, transform them by the leader's transform. What it actually does is it uses dead reckoning. So we'll try to anticipate where the offset is based on the speed of the leader, the speed of the followers. So that way they're able to maintain the formation much better. And this is really useful steering behavior for creating, for example, if you wanted to create birds that flew in a V formation. I've used this behavior for manta ray formations. You can also use it for formations of spaceships where you want them to stay in formation. And don't forget, all of these behaviors can be enabled, disabled. Well, not really enabled or disabled. They can be enabled or disabled, but they can also be added or removed from the voids at runtime. So what you see here as well is those purple lines in the game. Those purple lines, the start of the purple line is the original offset. So this is the offset relative to the leader, based on where these voids were when they started the scene. and the end of that line is like the dead reckoning. So I'm actually trying to seek the followers will try and seek the end of the line rather than the beginning of the line. And as the leader slows down, that purple line is going to get smaller because the dead reckoning function does not need to project forward so far. It's based on the speed of the leader. So yeah, the leader also is implementing two different types of wandering behaviors. Next example here, and this is a really cool example. And this is when people think about voids, this is often what they think of. I'm just going to make sure my recording is still going here. We're still going. Wonderful. Sound looks good. Okay, cool. So what we have here is when people think about voids, this is the classic voids simulation. So each autonomous agent, each void in this scene here, and there's 200 of them, is implementing avoidance, highest priority behavior, so they don't crash into each other. So they're doing their raycasts. It's also implementing a separation behavior. So separation was described by Craig Reynolds in his original paper as well. Separation basically, the void needs to know which voids in the environment are its neighbor voids. And once it knows which are the neighbor voids, then it says generate a force, which is proportional to how close I am to my neighbor, which is going to push me away from my neighbors. So very, very close, we're going to generate a big force. Quite far away, we generate a small force. And that's called separation. The second or the third behavior we see there is called alignment. And what alignment does, again, the void needs to know its neighbors. And when a void knows its neighbors, it can say, what is the average forward vector of the neighbors, and then generate a force from that. So that's called alignment. And then if you just use alignment by itself, the voids will all just line up like this, and they won't move too much. The next one then is cohesion. So cohesion, what happens is every void calculates the center of mass of its neighbors. So the average position of all the neighbors, and then the void tries to seek that position. And Craig Reynolds discovered if you add these three forces together, you get this lovely thing called flocking. In this world of autonomous agents and steering behaviors, it's called flocking. And flocking basically means separation, cohesion, alignment, and then they look like flocks of birds or schools of fish. And they have this beautiful hypnotic quality that you can just watch them. These also have the avoidance behavior as well, so they will avoid those big spheres which move through the environment as well, creating a bit of additional chaos. And you can see also the wander behavior and constraint behaviors are active as well. Constraint keeping it inside a sphere, and the wander behavior then adding a little bit of randomness into it as well. So a few things I can show you here. I can press, if I go over here back into the game, I can press C. C brings me back into the void first person camera perspective. Press C again, back into first person perspective. And I'm going to press P to pause the simulation, just to explain a few things about what's been visualized here. So what's been visualized here, obviously you can see all the voids. It looks so cool. And what we see here also is an algorithm called cell space partitioning. So this algorithm, the flocking algorithm, the way it's classically written is an ON squared algorithm. And in computer science, we don't like ON squared because it means that as we add one extra void, it's going to square the number of distance calculations that need to be made. So we don't like that. And so there's an algorithm you can use called cell space partitioning. And how that works is there's one pass through the scene. Every void is allocated a cell. And when a void needs to count its neighbors, it basically checks to see, okay, my neighbor distance is so much, how many cells overlap with the neighbor distance? And if a cell overlaps with the neighbor distance, then I look into that cell to see what voids are in the cell, and if they're, and then I basically use those as my neighbors. So this sort of reduces the complexity to n, sort of. But if they're all bunched up, they still need to do lots of distance calculations. So you kind of need to limit the number of neighbors. So that's the issue there. Cool. That is, let me just press P again. So this shows you the cell space partitioning algorithm. It illustrates how the cell space partitioning algorithm is creating these cells. The cells are a fixed size. It's a very, very nice and a very, very cool computer science algorithm with lots of lovely efficiencies. For example, to assign voids to cells, it's like one or two lines of code, and then you basically just take the cell, the void X, Y, and Z, divide by the cell size, and round down. So use the floor, and then that gives you one number, sort of thing. What else does it do? It uses either a map, so sparse data structure for the cells, or the other option is to use a multi-map. So you can use a multi-map, or you can use a map with an array. So let me just double check my video's still going here. Still recording, fantastic, just a bit paranoid and firing now. So what I wanted to show you, maybe if I go Control 2, I can show you, let's make sure that it's switched over. Yeah, switched over, great. So we're Control 2 here, and what I want to show you is, this is the school with avoidance. You can take the school here, and I can go and say turn off the partitioning algorithm. So if I turn off the partitioning algorithm, do I have to hit save? If I turn the partitioning algorithm off and hit save, I should see a reducing of the frame rate. So maybe I'll go Control 1, bring back that window again, to see what happens here. So partitioning on, saving, yeah, look at that. Partitioning on, I'm getting 28 FPS, 30 FPS sometimes. Partitioning off, saving, and 24, partitioning on, saving again. Great, yeah. So it's going up by about 5 FPS when I turn the partitioning algorithm on. So that's that cool algorithm illustrated there. Wonderful. All right, so what are we going to do here? I'm going to press C, oops, escape. Over here, press C, back into the camera mode. Oh wow, look at those lovely schools there. They look so cool. All right, next example, and I think this is the last one. No, this is 2 more examples to go. This example here is an example of turning on and turning off steering behavior. So I'm going to press C and C again to go into first person mode. And what I can do now is I'm going to press P to pause the voids, right, just so I can catch this void. And what I want to do is I want to enter into this dodecahedron shape which is attached to the void. When I enter into this dodecahedron shape, a few things are going to happen here. First of all, my position is going to lerp to the center, and also it removes the harmonic steering behavior from the void, and it instead attaches player steering. So what you could do here is if I press P to unpause, now I am controlling this. All right, so steer the void around here. Yeah, I'm in charge here. Void, I am now driving this void. So this is something you can use in VR. I've used it in VR and it feels really cool. Because you can do things like dragons, and you can fly in the back of the bird and stuff like this. And you can see that the void still has, because it's using weighted, truncated, prioritized, running some to some, prioritize and weight all of the behaviors. Yeah, it still can't crash into obstacles, or even if I try to steer too far out of the environment. Let's try that one. We will see that the constrain steering behavior is going to take over, and it will basically push me back in. Okay, whoa, come on, try and go. Whoa, so the void's constrained behavior, hopefully you got to see the constrained behavior. Increasing its magnitude there up in the top left-hand corner of the screen. When we go outside, you see constraint increasing. Look at that, and then I get pushed back inside. All right, let's go for the next example. Next example here is to show how these behaviors can be used to set up sort of scenarios, like gaming scenarios. And in this scenario here, I have 2 voids. One is designated as the attacker, and one is designated as the pig, the defender. So the attacker is going to launch from its base, as you can see, right? And its goal is to try and get to the target point, and then it's going to do a strafe run and come back. Okay, right? Let's get out of here. You can also hear here, this is, if you can hopefully hear, you can hear that every time they transition from one state to the next, the voice will play a sound. And you can see as well in the top left, you can see what state the void is in. So the attacker is in retreating state, and the pig is in the defense state. Okay, they also have a global state. Great. So yeah, the pig has gone to return to base. All right, so that is basically activated the seek steering behavior, sent it back to its base, and then when it gets to back to its base, it will again transition into different behavior, different state, which is going to be the attack state. So now the attacker is in attack, the pig is in the docked state. Okay, once the Cobra Mark III, once the attacker gets in range, it launches, goes into defend mode, and once the attacker goes out of range, it will go back into its return to base mode. Cool. So let me see. That's it. We're back to Seek again. All right, everybody. So that is all of the examples that I've created so far with miniature rotary phone. Loads of potential for this project. You could do space things. You could do nature things. And in fact, I gave this code to my students, and they did lots of nature sims as their assignment this year. And I'm going to include the link to the playlist of those assignment videos in the description, and also I will include the link to the GitHub. All the code for this project is available under MIT license, so by all means take this code and make some things out of it and have fun. And that's it, everybody. Thanks for watching.